decided to introduce. And Homanga, I'm going to apologize if I get your last name wrong. Homanga, this is difficult. Bharadwaj? Am I close, Homanga?
That's a bit far off, but that's fine. It's
Okay,
genuinely difficult.
I apologize. Maybe you can tell us. You can introduce yourself quickly and pronounce it properly. I apologize, indeed. Okay, so Homanga is with professors Shakurti and Garg at UTM, and is going to tell us today about conservative safety critics for exploration. So, Homanga, whenever you're ready, take it away. Thanks very much.
So imagine the task of training a quadruped agent from scratch. How do you ensure that the agent doesn't fall down during training and break itself? My name is Homanga, and I'm going to show you how. So reinforcement learning is a paradigm for learning-based control where an agent interacts with the environment, and the objective is to get better by collecting more data and optimizing a policy to achieve higher rewards. The rewards indicate a signal towards task completion. However, in robotics, we not only want the agent to complete the task, but do so safely without damaging itself and the environment. So what is safe exploration? So safe exploration is this idea of avoiding undesirable states in the environment that could lead to failures that are catastrophic in nature. For example, the robot breaking itself or breaking the environment or damaging the humans that are interacting with the robot. So consider the example that I mentioned previously. A quadruped agent needs to run as fast as possible. And the idea is that it shouldn't fall down during this process. We want it to be training from scratch, collecting data through trial and error learning, which is the reinforcement learning paradigm, but yet we want it to respect some safety constraints such that it doesn't fall. So our modification is to reinforcement learning by incorporating constraints. So conservative safety critics, in short CSC, learns a conservative estimate of how safe it is to execute a certain action in the environment at a certain state. In this way, by overestimating the probability of failure, that is by being conservative with respect to how safe it is, the agent resamples actions until a safe action is found and then executes that action in the environment. So the ultimate objective is to learn a policy that takes in a state as input and outputs an action. And our results demonstrate that we add this additional safety bit to reinforcement learning, and yet we can achieve near optimal convergence corresponding to the unconstrained reinforcement learning problem. And at the same time, we show that the probability of failures is bounded that traditional reinforcement learning fails to provide. Some additional examples that we consider in the paper are a car navigation by avoiding some traps in the environment and a robot arm that needs to push a block without the block toppling. So I hope that this framework for reinforcement learning enables safety critical real world applications useful for robotics. Thank you.